Hi, I'm Tommy Gröndal, and this presentation is about the employment of data augmentation on text classification in a toxic language dataset. This is joint work between Aalto University, the University of Waterloo, and Huawei Technologies. The purpose of data augmentation is to generate synthetic data to the original dataset to increase its size and variability. It's commonly applied to images, but has also shown promise in text. We compared a large number of data augmentation techniques for text, specifically in the task of toxic language classification. Our test setting is special compared to most other text classification tasks. First, we have very few training documents in the toxic class. Secondly, we have many more training data points in the non-toxic class, making the original training set highly imbalanced. We trained 4 classifiers on the original and augmented datasets. 2 logistic regression classifiers based on word or character n-grams, a convolutional network or CNN, and BERT, which is a large pre-trained transformer architecture that we fine-tuned on our training set. We used the toxic common classification dataset from Kaggle. We did binary classification for the threat label, but we also received similar results on another toxic class. As the training set, we used a 5% subset of the original Kaggle training set. We call this the seed dataset. The number of toxic data points with the threat label was very low in seed, only 25 comments. We then augmented the toxic class data points to 20 times the original size. We compared altogether 8 augmentation techniques to training on the seed data alone. Of these, 3 worked the best. The replacement of subword tokens with their byte pair embedding or BPM neighbors. Adding non-toxic sentences to the original toxic training documents. And using the pre-trained GPT-2 language model for generating new toxic documents. We first fine-tuned GPT-2 on the toxic documents in the seed training data, then prompted the fine-tuned GPT-2 on the original toxic document, and treated the first sentence generated by GPT-2 from this prompt as the new document. I'll summarize the main results from our experiments. When training on seed data alone, toxic class recall was very low or even non-existent. This means that the classifier was unable to detect almost any toxic class data points in the test set. In contrast, in the non-toxic class, both precision and recall were very high, and augmentation had no visible effect. Usually augmentation increased toxic class recall, sometimes more and sometimes less. This was usually countered by at least some negative effect on toxic class precision. However, with most techniques, their overall effect on the F-score, which is their harmonic mean, was positive. Regardless of classifier, GPT-2, add, and BPM replacements worked well. Combining these techniques together worked even better. The best overall performance was achieved by BERT with the add augmentation technique, where we included unrelated sentences to original toxic training documents. This managed to improve the original F-score by 21%. The downside of using BERT is its high computational requirements. Combining the add, BPM, and GPT-2 augmentation techniques allowed us to approximate BERT's performance with significantly less computational overhead. With GPT-2, the balance between toxic class precision and recall in the other 3 classifiers was better than that in BERT, resulting in a higher F-score. Combining add, BPM, and GPT-2 together improved the performance of the techniques over GPT-2 alone, and was the overall best augmentation technique across classifiers. Only add and BPM together also had decent success with most classifiers. Like BERT, GPT-2 requires GPU memory to run, but far less than BERT. Add and BPM can be run without GPU and have no significant memory or time requirements. Based on our results, we make the following recommendations. While BERT failed when training on seed alone, using the add augmentation technique resulted in the best overall F-score improvement. The problem with BERT is its high computational overhead. The combination of add, BPM, and GPT-2 on the other 3 classifiers were able to approximate BERT's behavior with less computational resources. However, GPT-2 still relies on a large pre-trained model and uses GPU memory. If neither BERT nor GPT-2 is available, the combination of add and BPM was the overall best option. Overall, we take these results to indicate the benefit of data augmentation in toxic language classification.